So, what am I going to do today? The first thing I'm going to do is review for you the main ideas in this qualitative method for trying to understand solutions of first-order autonomous equations. dy by dt is f of y, equation 27 in the notes. Namely, the right-hand side is only a function of the dependent variable. Okay? Now, some definitions. We say YE is a equilibrium solution if f of YE is 0. If f of YE is 0 and you start at YE exactly, then the dy by dt, which is equal to f of y, will be 0 there. And so y won't change. So if you start exactly at YE, you will stay there. Let's take this example here. dy by dt is y times 1 minus y times 2 minus y. We simply draw the graph of f of y, and here it is. Where are the three places? It's 0. 0, 1, and 2. They're the equilibrium points. The next natural question to ask is, if I start near, or I give this a little nudge away from YE, what will happen to y of t then? Will it return to YE? Or will it just stay in the neighborhood? Or will it go away? Okay? So, we have the definition. Leoponofstable first. It expresses in mathematics the idea that if you start near, you stay near. And we express it as follows. If you want to stay epsilon close to YE for all time, where epsilon is any small number but positive number, okay, then if you can find a place, if you can start within a delta of epsilon, as epsilon gets smaller, delta would get smaller. Think of delta might be like something like epsilon over 2 or 2 epsilon over 3. Then if you start this close to YE, you will stay that close within epsilon of YE for all time. That's the notion of Lyapunov-stable. All of the examples we see in first-order equations have a stronger stability. Good man. Find a seat there. But first of all, we say YE is unstable if it is not Lyapunov-stable. In other words, if you start near and the solution goes away, then the equilibrium point is unstable. If YE is Lyapunov-stable, and in addition, that if we start a little distance away from YE, we not only stay in the neighborhood, but actually tend back to YE as t goes to infinity, then we say that YE is asymptotically stable. That's a stronger stability, because not only do you just stay in the neighborhood, but you actually go back to the equilibrium point. An example we'll meet later of Lyapunov stability is the pendulum, the undamped pendulum. This is the stable equilibrium where the pendulum rod is hanging straight down. You give it a little nudge and it'll just swing forever in the neighborhood. That's Lyapunov stable. Okay? Unstable is if it starts up here, you give it a little nudge, it goes a long way away. Okay? So, these are the basic definitions. Finally, the notion of basin of attraction, of a stable, asymptotically stable equilibrium point, YE. It's the set of all initial conditions for which the solution starting there ends up at YE as t goes to infinity. Let's take a look at our examples. Here. Supposing we start near 1 here. Supposing we start here. Then f of y at this particular y value is positive. So that means dy by dt is greater than 0 at this particular y. Therefore, as t increases, y will increase. So things will move this way. So between 0 and 1, the solution will move towards 1. By the very same argument, if you start between 1 and 2, because at any y in here, f of y is negative, dy by dt is negative, as t increases, y decreases, the solution will move this way. If we're out here, the solution will move this way. And if we're out here, the solution will move this way. Okay? So now we can read off, is 0 stable or unstable? 0 is what? It's equilibrium, but is it a stable equilibrium or not unstable? Unstable, because if you start this side, you head off to 1. If you start this side, you head off to minus infinity. How about 2? Is it stable or unstable? Unstable, because once you start slightly to the side, you head away from that point. How about 1? Stable? It's asymptotically stable. What is its basin of attraction? Basin of attraction of YE equals 1 is the set of all starting points. Where would I have to start to end up at 1? Anywhere between 0 and 2. So it's this open set. So y of 0 would have to be greater than 0 and less than 2. That's the basin of attraction of the asymptotically stable point YE equals 1. Now, things are not always as simple as they might look from this example. How about this guy here? How about this example? The right-hand side is now y times 1 minus y all squared times 2 minus y. His graph looks like this. Okay? Does everybody see y? Because near y equals 1, it's a parabola. The graph is a parabola. Because near y equals 1, this is roughly 1, this is roughly 1, and so you look like you're graphing f of y equals 1 minus y squared in that neighborhood. So the graph both comes up and down. I mean, it goes down and then up here. All right, now, what are the equilibrium points? Okay, the equilibrium points are 0, 1, and 2. Now let's put in our arrows. If I start over here, if I start with any y of 0 less than 0, which direction will I go? To the left or to the right? To the left. Okay? If I start anywhere between 0 and 1, which will I go? Which way will I go? To the left or to the right? To the right, correct. If I start between 1 and 2, which way do I go? Between the left, do I go left or do I go right? Okay. And if I start out here, which way do I go? Now, would you like to tell me, first of all, 0, unstable or stable? Correct. 2, stable or unstable? Asymptotically stable. Right. 1. How many people think it's unstable? Get the hands right up. Yep, good. How many people think it's stable? And you say it's either. Could be either. There is a sense in which you're correct. But actually, if we think carefully about the definition, it's unstable. Why? Because the definition says, for Lyapunov stability to hold, I must be able to start near and stay near. I don't have to just start near on one side and stay near. I must be able to start near on both sides and stay near. Now, it's true that if I start, I'll answer your question in a minute. It's true if I start on this side, I will end back at 1. But if I happen to perturb to this side, I will end up at 2. So it's unstable because I'm not allowed any old perturbation. Only for a very special set of perturbations will it actually go back to the 1. So for general perturbation away from 1, it will be unstable. Some people in some books call this semi-stable. Okay. Semi-stable, it's like being half pregnant again. You had a question.
Yeah, I was wondering if you could give an example where the graph is not stable but not asymptotically stable.
No, I cannot give an example of that. That's a good question. I've told you that in first order equations, they're all either asymptotically stable or unstable. When we get to second order problems, we'll have equilibria where you can get oscillations in the neighborhood of the equilibrium point, and they will be Leoponofstable. A gentleman up here told me last time as an example of Lyapunov stability, he says, is the orbit of the sun, the Earth around the sun, is that Lyapunov stable? And the answer is, yes, it is. The orbit is Lyapunov stable, because if you give the sun or the Earth a little kick, its orbit will change very slightly. Okay, it'll stay in the neighborhood of the old orbit. Okay, now if you actually introduce a third body in there, then the whole problem gets very, very difficult, and very strange things can happen. So, in fact, Poincaré in the late 19th century wondered about this sort of thing. What would happen if you would have the two-body problem that everybody since Newton's time understood you'd have a nice elliptical orbit? Well, the question is, what happens if a Jupiter comes along and puts a perturbation? What will happen often is that you can say that the effect of Jupiter will not make much difference over very long times to the orbit of the Earth around the Sun, but you can't say for all time. Okay? So these problems get quite tricky. Very good. Very good. So now, do you feel that you have a fairly good idea how to handle autonomous first-order equations? Now, it doesn't substitute, this method doesn't substitute for getting an explicit solution, which I will expect you to be able to do by using the separable method, but you're much better off if your equation is autonomous, drawing yourself the graph, figuring out what's going to happen, and then if you need the precise trajectory of the x of t or the y of t, then you've got to go and do the hard work and actually solve it. Question?
Why doesn't the arrow on the right side why isn't it pointing to the right?
The arrow in this diagram, the one here, okay. The arrow points left here because for y of 0, if you start greater than 2, the f of y is negative. The graph is below the axis. Therefore, the corresponding dy by dt is negative. And therefore, as t increases, y will decrease. Question?
What is the basis of attraction for that semi-extension?
Ah, very good. I'm glad you brought that up because I meant to ask that. Can I put the challenge to you?
Yes, sir. Would the basis of attraction be like 1 is less than y2 less than 2?
Well, where can I definitely start to end up here? I'll have to be greater than 1 because if I start here, actually I'll end up at 1. And where can I start out on this side? Anywhere. So the basin of attraction of this solution is 1 to infinity. Thank you.
Did you say 1 has a basin of attraction?
1 is unstable. But yes, it's semi-stable in the sense that if I start between 0 and 1, I will end up at 1. That's true. But when I get to 1, if somebody should happen to come along or a little wind should blow me the wrong side, I won't stay there. Okay, so very good. The next thing we're going to do is apply these ideas to population dynamics. Population dynamics. Now, I'm going to let y of t be the number. It could be measured in singles or units of 1,000 or units of 1,000,000. It depends on what numbers we have. Be the number in a population of, we're going to look at different cases, people, rabbits, and deer. So, the first question, which is natural to ask, is the change, the rate of change of y. Let's not get too personal. So on the first example, we'll talk rabbits. Why does the population increase?
Because they reproduce.
They reproduce. 2 rabbits come together and meet and have little rabbits and so on. And what do you think the rate of increase depends upon?
Availability of food.
That's a little, he said the availability of food. We're going to come back to that. What we're saying, we're going to assume at the very beginning, the first approximation is food is limitless. So the rabbits are living in the Garden of Eden.
It'll depend on the number of existing rabbits and the virility of said rabbits?
Right, right. Let's assume that the virility proportion of virile rabbits is more or less constant, and so it's then depends on the number of rabbits in the population. Correct. It's true, there will be a death rate, but if the birth rate is greater than the death rate, the growth will be positive. Okay, so it's true, as this gentleman says, the rate of growth is proportional to the number of rabbits present, providing there's unlimited food, providing there's no hunting. We'll get to those points now in a minute. This law was proposed for the first time in 1798 by a general philosopher, economist, scientist, a man called Malthus. And if you look up Malthus in Google or Wikipedia, you can read a little bit about him. So it's called Malthuses Law. And it has a solution. Do I need to go through the solution method, or are you all comfortable so that the solution would be y of t is y of 0 e to the kt? Is everybody comfortable with that? How do we do that? It's separable. We divide across by y. We assume y isn't 0. Then we get dy over y as k dt. We integrate. I get log goalposts y. But since y is positive anyway, we'll just say it's log y. And that's equal to kt plus c. So then exponentiating, I get y is equal to some constant e to the kt. That constant is determined by the fact that at t equals 0, y is y of 0. And therefore I get this. So the first question I might ask is, how long does it take population to double? To double. Namely, at what y, y of t2, when is that twice y of 0? But y of t2, of course, is y of 0 e to the k times t2. Right? I'm asking for the time t2 when it takes y will be twice its original size. And since y of t2 is y of 0 e to the k of t2 by the solution, this is the same as this. Therefore, k times t2, the y's cancel. I get k times t2 equals log 2. So the population doubling time is log 2 over this growth rate. So I'm either given the growth rate, k, or the population doubling time. Very similar to in radioactive decay, when we had dy by dt is minus ky, we looked at what was the half time, the half-life, the time it took for y of t to go down to half of y of 0, because there the number was exponentially decaying. Here it is exponentially increasing. Have there been periods in history where this has happened? I'm sure it's happened for rabbits lots of times, but I'm thinking of people now. Can anybody remember? Yes. I think you're going to have to yell up. I'm a bit deaf. When technology started? Yes, yes, very true. In those periods, we did have exponential growth. And the most recent one, I think the baby boomers weren't quite exponential. The most recent one, though, dramatic one, was in Ireland. In 1800, the population of Ireland was 4 million. In 1845, it was 8 million. And if you draw a graph of the population in between, it is indeed quite exponential. Now, why is it? Can anybody come up with the reason that, for some reason, the resources became limitless at that time? Yes, who said that? Potatoes is correct. They didn't just help Ireland, they grew very well in Germany and everywhere, but they were brought back from the New World and by the explorers, Rayleigh among them, and they flourished. Why are potatoes very good for you? Not because you can make poutine from them, no. Because what? Yes, they're actually, because there's many different types, they can grow in very different climates and everything. Yes?
You can fry them and they taste quite good. It takes very little effort to grow.
I don't think they had French fries at that time. What was the problem with people's diet back in the 18th century, for example? What did they suffer from a lot? A lack of what? Well, scurvy was a big problem, especially on ships and things, right? Essentially, it's lack of vitamin C. And vitamin C, the vitamin C content of potato skins is quite high compared to the other parts of the diet, the other dietary components that the Irish had at that time. And the potatoes were also cheap, so the Irish were very poor, and so they found a source of reasonably cheap food. But now, of course, the trouble with relying on one crop or finite resource is this growth won't go on forever. Okay? As the population gets more and more and more, the call on the available resources is more stringent, and in fact the growth rate tends to even off. And so this is modeled by a thing called the Logistic Equation. Essentially, the growth rate, instead of being pure constant, starts to decrease the closer the population gets to some saturation level. So this is known as the Logistic Equation. So now let us examine the Logistic Equation and see what we can learn from it. Would you all draw the graph of the right-hand side there, please? It's a first-order autonomous equation, so we should be able to use what we have learned last day and early today. What does this graph look like? As a function of y. And we really are only interested in y positive. So, what's it going to look like? near 0, which way is the graph going to go? Up, right, because it roughly, for y very small, it looks like ky. And then what happens as y gets to be, say, 2k? It goes negative. So it has to come down, and it has a 0 at k. Okay, so now, yes. Yes. This k is the growth rate. This k is some, as we'll see, we'll interpret it as a saturation level. Supposing I'm to start, supposing the population starts here. Will the population increase or decrease with time? It'll increase, because here the graph is positive, dy by dt is positive, y increases as t increases. So I move that way. How about if I'm here? I decrease. So, of the two equilibria, 0 and capital K, which one is unstable and which one is stable? Capital K, this one is asymptotically stable. So asymptotically stable. With basin of attraction, we're only dealing with positive y's because we're talking population, 0 to infinity. In other words, every starting point will end up at k. If you start with too much population for the resources present, that the 1 minus y over k will be negative, and dy by dt will decrease. It'll stop decreasing when y gets to k. Likewise, if you start less than this amount, capital K, dy by dt will be positive, y will increase as t increases, until y gets up to k, then it stops. So this is called the saturation level. In some sense, we could think in Ireland's case, the doubling time was about 45 years. Took 45 years for the population to go from 4 million to 8 million. And roughly speaking, the amount of people the countryside could hold with the amount of resources available for food was 8 million. Now, let's switch to deer. We have an ecological environment, a forest, nice forest, lots of good chewy greens. So a small population of deer will move in and it will grow according to the Malthuses Law. But then eventually deer can be quite prolific as well. So the deer population grows until it begins to strain the amount of resources. But there's still too many deer. How many people live near a place where there's lots of deer? And have you ever driven at night? And have you ever had a deer jump out at you in front of you? You have? Yeah, I've had that too. So you managed to stop, or did you eat him later? No. Yeah, but it can kill you because he can come through the windscreen in a hurry. So actually, we have to cull. It makes sense as an ecological strategy to keep the population at reasonable numbers to cull. So how do we cull deer? Right?
Permit hunting.
Yes, we issue hunting licenses. We say so many deer can be taken out of the population per year. So we model that by putting in, this is the logistic equation now with hunting. Okay. Now, H, in the notes actually I write H as positive. I mean I write it as plus H and then say it's negative because we're taking deer out of the population, not putting it in. But here I'm going to write it as minus H just to make it clear that it's a loss. So H is a constant. It says how many deer I expect to be taken out of the population per time unit, and now we're going to talk years, by hunters. So, is this a good strategy? Tell me what happens to the graph. I want you to draw the graph now with the H in there. Think of it as small first. So tell me what happens this graph when H becomes positive, so minus H becomes a loss. What's going to happen that graph? Well, what is y? What is the right-hand side at y equals 0? We want to draw, what is it? Minus h. So it starts off at minus h. Right? So now what does it do from this starting point? Does it increase or decrease from here? It increases. So it does something like this. Now these 2 points, the equilibrium points, now are given by these 2 equilibrium points are ye plus and minus. They're a half k, capital K, plus or minus a half times k, 1 minus 4h over k times k. Did I need to be a genius to get that? Not at all. It's solving the quadratic equation. Right? I'm solving the quadratic equation. Y squared minus ky plus h over k. Is that correct? H times capital K over k equals 0. I'm solving that to get the 2 roots. Is that okay? It's just finding these 2 roots. So this is ye negative, and this is ye positive. Okay, now, yes?
Wouldn't it be if you multiplied the dy dt up there into the form of a quadratic equation, dy squared term be the one that involves k?
Well, here what I've done is it's minus h plus little ky minus ky over capital K, or ky squared over capital K. I multiplied across that equation by minus capital K over little k. Then I get that. So it's just, but you could tell from the graph that it's going to be a little bit less than capital K on the right and a little bit greater than 0 on the left. So now tell me, what's the situation? If I start in here, under the blue, which way will it go if I'm in between here and here? Will I go to the right or to the left? Right. How about if I start to the left here?
Left.
Left. And how about if I start over here? left. Okay? So now, who is the stable and who is the unstable equilibrium? YE plus is asymptotically stable, YE minus is unstable. Supposing I were to give a few more permits out. I mean, I'm happy. I mean, I have a deer population which is now saturating at YE plus. I'd like to bring it down a bit. That's too many. I'm still meeting them on the road at night. So I increase H. What bad things can happen? What's going to happen? What's going to happen, the graph? Think of little k and big K as being the same, and I increase the size of H. Yes?
Eventually your equilibrium points are going to meet the graph.
Very good. Eventually, I'm going to have them meet like this and then disappear. Now, if they meet or disappear, what's going to happen if I start at any y? I'm going to end up at 0. I'm going to get rid of the whole population. So I have a very little leeway just from here to here. If I pick the H slightly too much, bang, I lose the whole deer population. So you have to be careful in designing these strategies. What's the critical H? What's the critical H at which the two roots merge into each other and disappear, become complex effectively? What's the value of H? What's the value of H at which you get a double root? If you're going to get a double root, what's this got to be? 0. So what's the value of H? H would be K times capital K over 4. And does it have the right units? This is the units of population. That's per time. So this is population per time. And that's indeed the units of H, the number of permits per year that you issue. Let's go back to the Irish question. Now we're people again. And H is emigration. H is emigration. What would be if capital K in the Irish case was log 2 over 45 years, the period doubling time is roughly 45 years. So log 2 over 45. The capital K was 8 million. And I have divided by 4. Roughly what is that figure? So I want you to, 4 into 8 is 2. So what, I have 2 log 2 is what, 0.69 or 0.7, so that's 1.4 over 45 of a million. Our units is a million. So we're talking about 30,000. So if you had an emigration from Ireland of 30,000 a year, starting from 1845 on, where's the population of Ireland going to go eventually? Down to 0. Right. Now things change, of course. What happens is the H, this is what happened. Of course, there was a great emigration from Ireland, and the population came from 8 million gradually down, and it's actually only 4 million today. But of course, when it reaches an equilibrium again, because people stop emigrating when there comes enough resources and everything to sustain the population. Question?
I kind of got confused over here because I thought at the beginning that both k's are the same thing, but
No, I've told no. This k, this little k is the time rate of change of the population growth. Okay, the initial population growth if there was no unlimited resources. So that's a rate of change of growth. Capital K is the amount of population that can be sustained with no hunting or no losses. Okay, question?
I was just wondering why did you solve for H?
Why did I solve for H? Because I saw the great danger. I'm given this job of managing this pristine forest with lovely deer in it, and I'm encouraged to give out permits, hunting permits. Now, if I screw up and give out too many of them, a few years there'll be no deer, no job, goodbye. Right? So you have to be, you see, you are trying to figure out, H here is the value at which you lose any equilibria at all. Once H gets to be this big or bigger, the graph of that right-hand side falls below the axis. It's always negative. See that? And therefore, your population will just decrease till it hits 0. Question?
Can you say again what you times the ratio of 55 to get it into that quadratic formula?
How did I get this formula? Okay, it's the right-hand side. This is this is minus h plus little k times y minus little k over capital K times y squared. I want to know where that's 0. And then I just take out the minus k over k from here, and I put this equal to 0. So that's where the right-hand side is 0. You're solving a quadratic equation. Okay, so now, later on in the term, we're going to introduce another little twist into this game. The population Y is going to be rabbits, and we're going to introduce a population X, which are foxes. So not only will the rabbits get decreased by saturating or maybe by hunting, but also they'll run into the occasional fox and disappear that way. Foxes, on the other hand, will die out without rabbits. So left to themselves, the fox population would exponentially decay. But fortunately, they meet a rabbit every now and again, and that sustains their population. So we look at this interaction between foxes and rabbits. And it's actually very interesting. You're going to find, I'll give you some data to look at. You know, what was it, the lynx and some prey in Canada, they had graphs of this was the prey population had something like that was their graph, and the predators were like this, sort of like this. And at one stage in one of these cycles, people were very worried because the number of I forget what it was, the number of the prey population got very low. But in fact, it was just part of a natural oscillation. So we'll understand that from the mathematics. We'll see that this is okay, this is all right. As long as we don't get these graphs dipping down below the 0, we're okay. But you see, designing ecological strategies can be done with very simple differential equations. Right. Now, we come to the second piece of the menu today, and that's the following. I'm going to teach you how to solve first order ODEs. Okay, first order. So it's dy by dx plus p of xy equals q of x. In other words, in the general case, our f of x and y was minus p of x times y plus q of x. So you see, the equation is entirely linear. It's a linear combination of 1, y, and dy by dx. The coefficients in the combination can be functions of the independent variable. Right. How do you solve this? Step 1. Integrating factor. We create an integrating factor. Call it IF, and it's simply e to the integral from any constant up to x of p of t prime dt prime. Oh, where did we see that one before? Step 2. We multiply, this now is equation 3.1, I believe. We multiply 3.1 by the integrating factor. What will I get? I'll get e to the integral a to x p of t prime dt prime. T prime is just a dummy variable of integration, times dy by dx, plus p of x times e to the integral a to x of p of t prime dt prime, times y, equals q of x, e to the integral a to x of p of t prime dt prime. Now, it looks as if I'm making things more complicated rather than less complicated, because I've introduced this integrating factor and it's pretty messy. But from your graded homework number 1, and I think you also had it on your quiz number 1, what is this guy here? This guy here is nothing other but d by dx of the integrating factor. Whoops. See, this guy, that product, is just the d by dx of e to the integral from a up to x of p of t prime dt prime. So now I have integrating factor times dy by dx plus the d by dx of the integrating factor times y equals something that's known over here. Can anybody spot what's nice about the left-hand side? Well, no, because I don't want to do that. There's something nicer about it. Yes?
Like derivative first term equals
What's the rule of the derivative of a product? D by dx of u times v is what?
U1
So it's
u prime v plus v prime u.
Right. It's v du by dx plus u dv by dx. But that's exactly what we have here. We have integrating factor times dy by dx plus y times the d by dx of the integrating factor. So this is just the left-hand side. So recognize the left-hand side is just the total d by dx of y times the integrating factor. So both of those terms are just this. Let me just emphasize that by ringing them both. All of this, that's just by the product rule. It's just the d by dx, the perfect derivative of y times the integrating factor. And that's equal to something known, which is this. Q of x e to the a to x p of t prime dt prime. So now what do? I just integrate, right? I get step 4, integrate. See, I can integrate both sides. Left-hand side is y e to the a to x p of t prime dt prime equals some constant plus integral of all this. It'll be some b up to x, and we'll introduce the letter s to stand for the x, the dummy variable of integration here, e to the integral a to s p of t prime dt prime ds. Finished. Explicit solution for y. Right, so now let's do an example. Let's do an example. So, I'm going to go back to a mixing problem. And I'm going to have 2 gallons per minute coming in. Each gallon contains 1 pound. Into a tank, well mixed. The only difference is out will come 1 gallon. The starting amount is 10 gallons. And we'll say initially no salt. All right? So now, after a time t, what's the total volume in the tank? The volume in the tank at time t, after t minutes, the starting volume is 10. You're putting in 2 gallons a minute and taking out 1. So it's 10 plus t. That clear? 10 plus t. Right? Because you start with 10, 2 gallons a minute are going in, 1 gallon a minute is coming out, so you're going to be left with 10 plus 2 minus 1 t after t minutes. X of t is the number of pounds of salt at t minutes. And the concentration at any time is x of t over v of t. All right, now what's our equation? It's dx by dt is what goes in. It's 2, and the concentration is 1. So 2 gallons per minute. Each gallon contains 1 pound. What comes out, the rate of coming out is 1 times the concentration coming out. It's x over 10 plus t. So this is the equation dx by dt plus 1 over 10 plus t times x equals 2. and the starting number of pounds of salt was 0. So this is a linear equation. Now the y has become x and the x has become t. So first step. But you see, this depends upon the independent variable, so it's not a separable equation. I can't use the separable method. So I have to create an integrating factor. Step 1. The integrating factor is e to the integral of 1 over 10 plus t dt. What is that? What is the integral of dt over 10 plus t? Log 10 plus t. And because it's positive, we don't have to put in the goalposts. So it's e to the log, so it's just 10 plus t. Okay? So now I multiply across by the integrating factor. Step 2. 10 plus t times dy by dt plus 10 plus t times 10 plus t is 1. 1 times x dx by dt plus x equals, on the right hand side, 2 times 10 plus t. Yes?
So you only multiply by what's inside
No, I multiply by whatever this turns out to be. This is e to the log of 10 plus t. E to the log of 10 plus t is 10 plus t. So that's e to the log of 10 plus t. Now, I recognize the left-hand side is a perfect derivative. Step 3. The left-hand side is just the d by dt of x times 10 plus t. And that's equal to 2 times 10 plus t. Now I integrate. Step 4, integrate. Integrate. I get x times 10 plus t equals, now I can integrate this by taking these two things separately, but I'm just going to integrate the whole 10 plus t, which is be 10 plus t all squared over 2. We're adding a free constant anyway, so it's just 10 plus t all squared plus a constant. Question?
At step 1, where you introduce your integration factor, why isn't the x a part?
Why? Because, remember, t is the independent variable now. It's the x up here. Okay? So it's just dt over 10 plus t. Or dx over p of x dx. Okay? Now, to solve this, to get the c at t equals 0, x of 0 is 0, and so therefore c is minus 100. So therefore x of t, dividing across by the 10 plus t, will be 10 plus t minus 100 over 10 plus t. The concentration, which is x of t over 10 plus t, will be 1 minus 1 over 1 plus t over 10 all squared. I divided above and below by the 100. And that's an explicit solution. The concentration will eventually go to 1, as we expect. But this time things are a little different. First of all, the decay is not exponential, it's algebraic. Instead of being e to the minus something t, decaying to the equilibrium solution, it just goes down like 1 over 1 plus t over 10 all squared. Yeah.
What do you do from step 2 to 3?
Step 2 to 3, I recognize that this guy, by the product rule, is just the derivative of that product. It's exactly the equivalent of this step here. Okay. So now, let me see how many I've set here. Yes, there's a few examples here. You can try several of the examples here will be you will do by the solving the linear equations using integrating factor. So we've now learned 4 methods. We'll do lots more examples. We've now learned all the methodology we're going to learn for first order equations. Next day I'm going to talk about difference equations and Euler approximations. Hang on to your seats for a minute. And then I'm going to do 2 weeks worth of applications. And essentially for the first exam you're responsible for everything first order. Question? Yes. You take the coefficient of him and you take the exponential of his integral. 7:15 tomorrow, 8 o'clock Thursday in room Math 501.